welcome to Beyond the Qubit. Today I have Jelmer Renema from QuiX Quantum. And Jelmer is a very exciting guest because Jelmer knows everything about photonic quantum computers. And he recently had a paper about below the threshold on error correction. And that is a significant breakthrough for QuiX Quantum photonics quantum computer. When I interviewed Stefan in November 2024, he talked about a few data points. Could you walk us through the audience, maybe a small recap? What is the progress that QuiX Quantum made since then? And at that point, he was talking about 8 qubits and 64 qubits, and the 64 qubits being the error-corrected one. Improvements. So let's talk about improvements in physical qubits, improvements in the interferometer, improvements in the control stack, the PACU unit, and maybe a little bit. Okay, why do you need low speed phase shifters and why do you need high speed? And the progress in the feed-forward control unit, and the integration of the photon detector on chip or standalone, and the improvements on the error correction ratio. A lot to discuss, but maybe let's take it point by point.
Yeah. I think where I would like to start is with the last one, which is error correction. So what we have done at QuiX for the first time in photonics, and I do not want to undersell how big a deal this is we have for the first time built a device that uses photons where you can send something in that is somewhat quantum and something comes out that is more quantum. And what do I mean when I say somewhat quantum and more quantum? I mean the amount of errors that it has, or how far away it is from being the quantum system that you need to continue with the rest of the computer. Right?
And Jelmer, maybe before we go into it, can you maybe give a short recap for the audience that's not so technically knowledgeable on photonics, quantum computers? What is the difference between like a neutral atom or a superconducting and a photonics quantum computing? And especially, why does it matter if you have stationary qubits or moving qubits? Because I think that also impacts your answer on the quantum error correction. Very, very short, very basic recap why it matters for error correction.
Sure. So photonic quantum computers have what is called flying qubits. So photons are particles of light. They move at the speed of light. And therefore, it doesn't really make sense to try and build a conventional quantum computer where you identify the qubits with certain places on the chip, right? So in a photonic quantum computer, there isn't a place where you can point to and say, this is where qubit number 627 sits, right? So instead, the photons move through the chip all the time, and you build up entanglement in such a way that making measurements on these photons is equivalent to doing a quantum computation. So this is a little bit this is very non-obvious and quite subtle. But I think the easiest way to think about it is every layer of photons. So you have a bunch of devices that make photons. Then you have an optical circuit that makes entanglement between these photons. And then you make entanglement between, so all of these sources fire, they make photons. The photons go through the circuit, the sources fire again, they make more photons. So you kind of have different time steps. And these time steps you entangle between each other. And now you can make quantum information jump from one time step to the next. So from one round of photon generation to the next round of photon generation by doing measurements. And so, perhaps a bit surprising to hear, but a photonic quantum computer is a device that uses quantum teleportation as its elementary operation, right? So for us, quantum teleportation is sort of the basic building block of the computer. That's almost how you can think of it. And if you want maybe a little bit easier analogy, it's a little bit like that one level in Super Mario where you have to jump from platform to platform to platform, and every time that you jump on a platform, it starts sinking to the bottom of the screen, right? So Mario is the quantum information that is jumping from one layer to the next, and every time that he lands on one layer, that layer disappears. But if you jump fast enough, you can still make it from one end of the level to the other end of the level. That's kind of how you should imagine how a photonic quantum computer works. And so nothing is static, right? That's the important part here. And what is also really important is that a lot of operations are probabilistic. So with photonics, you cannot force two photons to interact with each other. So what you have to do is you have to try a bunch of times in parallel and then select the ones that were successful. And this works, but this means that you basically think of and then the ones that succeed, you send to the rest of the computer. So it's this kind of, you try many times in parallel, and the ones that succeed, you continue with. And if you think that through, that basically means that the whole computer has kind of the logical structure of, if you want, of a pyramid, right? So at the base, there are lots and lots and lots of single photon sources. Those single photon sources get combined into, right? The photons from those single photon sources get combined into small resource states, small entangled states of photons that you can do something useful with. And then you basically build up the entanglement into this form that you need to do this trick that I was talking about earlier with the Super Mario level, right? Where you sort of have different layers and the information jumps. You want to get to that structure, and you build up that structure by doing entangling operations. And at every layer, because it occasionally fails, you lose some of it, right? And so, as I said, it's a kind of pyramid where you have lots of cheap resources at the bottom. And as you go up the pyramid, gradually the resources become bigger and bigger, but you have fewer and fewer of them until you eventually get to this big state where you can do this measurement teleportation trick to do the calculation. And that's really a completely different way of thinking about how to build a quantum computer than if you're doing other technologies. But for photonics, it's the right way to do it.
Yes.
And so in that context, you also have to do error correction, but your error correction happens at the end, right? So your error correction is normally a part of the computation that you are running. And so in this protocol, in this way of doing things, error correction gives you an overhead, right? Well, it always gives you an overhead, but it gives you an overhead in this case also. So you need to take into account when you're building this state that you're going to want to do error correction on it at some point. And therefore it needs to be, depending on how much errors you want to correct, it needs to be bigger, or it needs to be way bigger than the state that you would have had to have if there were no errors. Now, in every quantum computer has errors, right? So error correction is sort of the ability to fix errors in a quantum computer is the defining technological milestone that eventually allows you to scale, right? So it is the defining technological problem that you must overcome to go to large-scale systems. And what we have done is we have basically moved this further down this stack. So we have invented a form of error correction, if you want, technically error mitigation, but explaining the difference between that is a little bit beyond the discussion here. So we have invented a way to reduce the errors that goes almost at the bottom of the pyramid. So you make these photons, and they are maybe not as good as you want them to be, and then you immediately send them into a little device that turns them into better photons, and then you start the rest of the computer. And because you do this early on, we can show that this is a way better strategy than trying to fix the problems at the end. Right?
Is it maybe, to summarize, is it correct to say that you lower the losses, because in the lowest layer you make sure that you have higher quality photons?
No, you don't. No, so you don't lower the losses. You lower. So this protocol works works on the indistinguishability error. So it works on the fact that the photons that you in practice do not have full control over how the photons get made in your photon sources. And for the photonic quantum computer to work, you need that. You need them to all be exactly what you aim them to be. And they come out as slightly different. And that can be, for example, in polarization or in color or in time of arrival, right? Because you will have eventually in this computer thousands of photon sources running in parallel. So you cannot, keep an eye on them all one by one. And so you get photons that are of lower quality than you want, maybe. Mm-hmm. You would want them to be perfect, of course, but you get them with some quality.
What is a perfect photon? Are they then all the same, all similar?
Yes. So a perfect photon is a photon that is in exactly the same quantum state as all of the other photons in your computer. So the same.
And what causes differences in photons? Is it difference in a laser, or is it differences controlled by the control and measurement electronics, or differences in temperature, or difference in chip manufacturing, or
it can be any of the thing. It can be any of the things that you mentioned. So you make these photons by pumping some kind of material with a laser, and the frequency with which you pump that laser, right? The frequency of that laser translates into the frequency of the photons that you make. And so you can imagine that if the frequency of this laser, which of course you're going to try and stabilize, right? But you can never stabilize it perfectly. So imagine that as your computer is running, you're making these photons. This laser drifts around a little bit. And so if the frequency is a little bit higher, it makes photons with a little bit higher frequency. If the frequency is lower, it makes photons with a little bit lower frequency. It can be other things as well. It can be indeed fabrication on the chip, right? So you can imagine that you make 1,000 photon sources. They all don't come out quite the same. It can be imperfections in your control electronics, right? So you're maybe trying to switch something, and I don't know, there is some kind of fault, and therefore you don't switch fast enough, and you cut off some part of the photon, right? Now you have a photon with a different kind of shape that is making its way through the system.
And one question that pops up, Jelmer, is that now with AI, with co-packaged optics, the industry is moving really forward on photonics, not at the same precision, not at the same losses as quantum, but do you benefit from a more mature photonic ecosystem? Does that bring cost down, or does it lead to more talent, or other benefits? And then I want to come back to the error correction.
Yes. So I would say yes, absolutely, right? So the requirements of a photonic quantum computer are you really need the world's most high-end photonics available, and then on certain numbers you even need to go beyond that, right? So quantum is really pushing the technology boundaries of what is possible in photonics. But of course, it doesn't hurt that there is an enormous amount of money that has alternative uses for those kinds of technologies. And then indeed, particularly AI is a big application domain.
Okay, back to the error correction where we start.
Sure. Yeah, okay. So you have these photons that are not all exactly how you want them to be. And what we have now shown is we have shown a little circuit where you send in a few photons, and the photons take a majority vote of what they should look like, so what state they should be in, and then one photon comes out that follows that majority vote. So that follows the kind of the average of the states that the other photons are in. And this is really good because it pulls all of the photons towards the target that you defined, right? And so what we showed is that this allows you to build a quantum computer. If you use this technique, which we called photon distillation, it allows you to build a quantum computer which is way more resource efficient than you would otherwise have been able to do, right? So if you think again back to this metaphor of this pyramid, like the pyramid goes up at some angle, because in every step you lose something, because every step you try to build a more complex thing and it sometimes fails. And basically what we showed is that if you use this technique, right, so it's kind of like you're building this pyramid and the bricks at the bottom are stronger, and therefore you can build the pyramid more steep, right? So at the end at the top, you end up with more resources, so you can build a bigger quantum computer with the same amount of photons. You can build a more powerful quantum computer with the same amount of photons, or equivalently, you can get the same amount of quantum computing power with a lower bill of materials.
Wow.
And we estimate that the reduction in costs is at least a factor of 4, although I want to emphasize that factor of 4 is a very conservative estimate that is limited by the quality of our model. And we have set up the model in such a way that we can only underestimate how much we win, right? So it's certainly a factor of 4, but it can be more. But we think it likely that it will be more than that, right? So this gives us a unique competitive advantage over all of our competitors in photonics.
Why can they not copy you? What would be hard for them? You've written the paper, you've outlaid the concept. Why is it hard for them to copy it? Is it patented, or do you have secret recipes, or what is difficult for them? Just say, well, QuiX is right on silicon nitride, on triplex. They're right on the error correction method. Let's just copy them.
I mean,
and we have better access to capital, and we beat them in that way. What prevents them from doing that?
I mean, of course it's patented, right? Why would we not patent it? I'm frankly a little bit surprised by the question. Now, we have, of course, protected this technology. And of course, we have also protected silicon nitride, right? So QuiX's patent position extends, and this is again consistent with what I was saying earlier, that our belief has always been that you must capture as much value in the entire stack as possible in order to be viable long term. So QuiX's patent position extends along that entire stack, right? So we have patents going all the way from proprietary quantum algorithms to all the way down to patents on the material technology, right? On the platform technology.
Okay, so purely from a patent perspective, it's very difficult to copy QuiX. But then I think there's also, you've been living and day and night about photonics quantum computing, and you have a lot of operational expertise. I think that is also very important. Is it maybe fair to say there are multiple ways of scaling quantum computers? So if I make an analogy to AI, there you have scale up, so increasing the amount of qubits per cluster. Secondly, you have scale out, forming clusters of qubit chips. And the third one is the error correction ratio from physical to logical qubits. You mentioned you made important progress on the physical to logical qubit error correction ratio. One of the benefits of photonics quantum computers is it scales very good in making the amount of clusters. But can you also explain? So, but what I'm wondering is, I think if I hear you, Jelmer, is what you explain is because of the silicon nitride, and because of what you explained with the indistinguishability and the pyramid, is that you are better you do the difficult things first. Is that fair to say? Whereas maybe PsiQuantum, they go directly to interconnect and scaling the amount of clusters, but then later on they maybe have to do the hard part. Is that fair to say, or can you give some context on that? You're much better informed on that than I am.
No, I think you have the right sense here, and I would not even particularly point to Psi there, but I would rather point to a lot of other players in Europe. So what a lot of players in Europe have done is they have tried to basically take purely this photonic chip, right, that we have made, and in some cases it's even been chips that we have provided, and try to build a purely probabilistic quantum computer around that, right? And so there's a subtlety here that this thing that you cannot deterministically, like you cannot force two photons to interact, as I was saying earlier. And that basically means that if you just take a bunch of photons and you throw them through some optical system, then the chance that they will behave like a useful quantum computer goes down exponentially as you increase the number of photons. And there is a big except there, except if you allow yourself to switch what some of the photons are doing based on some measurements on the other photons. So if you build a quantum computer out of photons that is purely, I throw some photons into an optical system and I see where they come out, that is just not a way to get to a useful quantum computer. And if you look at what a lot of our competitors on the European scene are doing, is they're doing exactly that, right? And that allows you to get to some numbers it allows you to get to some numbers early on. And especially the longer you're willing to wait, the higher your numbers can be. But we have always believed, as you said, in doing the hard things first. And so we have focused on making that switching step, right? So this is, in technical terms, this is called feed forward, right? So it's a bit like you see a train come past on one track, and then you very quickly run to another track and you throw a switch, right? So that some second train that is coming in goes in some other direction, right? So it's the ability to change your optical circuit based on what you have seen happen before, right? So I see some photons come by, where do they go? Okay, now I need to change the circuit so that the second round of photons goes in the right way. That's kind of what you need. And if you have that, then you can get around this problem of not being able to force the photons to interact. And that is exactly the hard piece of engineering that we have done. And then for that, you need fast feed forward. So then it comes back again to this technological achievement of this feed forward control unit. And that is exactly what the computer that we are delivering to the German Aerospace Agency will be the first computer, right? The first photonic quantum computer that is delivered to a customer that can do exactly that, right? So it will be a computer that has this feed-forward capability, which makes it a universal quantum computer.
What is the timing, Jelmer, of the computer? Because when I interviewed Stefan, that was 2027. How are you on track for that? For the 64
I would
qubit,
say, I would say the first delivery, the first delivery is literally happening as we speak. So I do not want to say too much about that, except watch this space. And be fast in converting this podcast into a video, because otherwise this part of the story may already be outdated by the time it goes online.
Yeah, probably. It might take. I have a few interviews before. I think for the audience, what is interesting is, Jelmer, I had the interview with Stefan in November 2024. What progress has been made? We talked about certain parts, but can you maybe summarize in a 2-minute recap? What is the biggest progress that QuiX Quantum made the last 1 year on important bottlenecks?
Sure. I would say we have hit all of our targets there, right? So we have hit the goals for improving the components, right? So we have increased quality of our photonic chips. We have demonstrated the electronics in our electronics control unit that will control the large-scale quantum computer. We have demonstrated the feed-forward control unit that has the fast electronics that you need to turn a non-universal quantum computer into a universal quantum computer. We have demonstrated this error correction thing, which is a first for photonics, and by the way, also a first for the Netherlands. So again, photonics is leading the quantum revolution in the Netherlands. And finally, we have hit this commercial target of delivering a quantum computer to our customer, right? So with all of those things, I would say we are doing amazingly.
Wow. And what is on your radar for the coming 5 years? Jelmer, what do you want? What is your inner voice now telling you? What do you want to work on for the coming 5 years?
So I would say the coming 5 years will be the crucial years that determine the future of the quantum industry. And I think that is the case because we will start to see business relationships solidify, right? So we will get to the point where there will be a more and more clear differentiation between the winners and the losers in the market. And the winners will also be more clear on who the people are that they want to work with in the long run, right? So there's going to be this enormous winnowing of the number of business relationships. And that is going to mean that people who think that they have something now may be left with nothing in 5 years, right? And so this consolidation, there's a consolidation going to happen in the industry, and that is going to be quite disruptive, right? And so we, I think, as a country, have to figure out how we're going to deal with that, right? So what are we as the Netherlands going to do to make sure that when that consolidation happens, that we are a part of that, that we come out on top, right? But of course, the same holds for QuiX, right? And we are in a good place, right? We really see that this strategy of building up, of sort of integrating ourselves along the entire stack, that is really paying off, right? Because as we discussed earlier, that puts us in a really central position where we can really coordinate these different technological parts and really make that the whole is more than the sum of its parts. So I think that is, on the business side, I think that is the clear, the end game is coming, and we have to figure out how to navigate that end game. And then on the technological side, I think as we are approaching this end game, it is also really interesting. It will also really be interesting to see what technologies will make it and which ones not, right? So within photonics, there might be a little bit of a standards war, let's say, where people that have different ideas on what material you should use for what, and so on and so forth, we will get to figure out, we will get to find out who is right in the next 5 years, right? And that, I would say that is one of the places where our early go-to-market strategy has helped a lot, because we have business relationships with a lot of the parties that are on the different technology platforms, right? So that is going to be interesting both from the business side and from the technology side to see how that is going to be navigated.
Okay, that's clear. Many things pop up, but let's leave it here. Thank you. And you specifically, what for example, you mentioned the Netherlands have to think about, okay, what role do they want to play, and how could the Dutch government or the Netherlands, how could they help you? How could they help QuiX Quantum?
Well, certainly, and this has been a discussion that has been going on in many fora for already a long time, is the purchase of a quantum computer, right? So I think there the call to action is quite clear. Just buy one, right? We have them on offer, and the coalition agreement says that the Dutch government wants to purchase a quantum computer. QuiX is the only company in the Netherlands that has actually delivered a full quantum computer to a customer. So we would be happy to provide one to the Dutch government as well.
And what is the battle here? Is if they buy a superconducting quantum computer or a photonics quantum computer? Is that the battle, Jelmer?
Why not both?
Yeah.
Right? I mean, at this point,
yeah.
No, seriously, right? I mean, I think the discussion, It's a very simple answer. Why not both?
Yeah, and I think it makes a lot of sense, especially for the long-term competitiveness of the Netherlands.
Well, I mean, there I should say that there's more to it than technology, right? And QuiX's role as a systems integrator really puts us in a unique position also in the Netherlands. And this is also something that is increasingly being recognized by the people that monitor these ecosystems on behalf of the Dutch government. So if you sort of look in the various reports, it's very clear that this special position which we have carved out for ourselves is more and more being recognized, and that people are really beginning to realize that QuiX really represents a unique opportunity for the Dutch government.
Mm-hmm.
And I do want to say there, I want to make it very clear that that is not an argument, that's not an argument for autarky, right? I do want to make that very clear. I want to make it clear that that is not, again, to say, you know, we should lock the doors and only come out when we have the computer. That computer will involve business relationships across Europe. It will involve business relationships across NATO and even outside of that with sort of allied third-party countries. But I think what we have learned from other technologies that the Netherlands is involved in is that you can really only have a role in that if you operate from a position of strength, and that the way for the Netherlands to get that position of strength is to come in as high as possible in the value chain and to integrate as much as possible as we can, because that is what we in the Netherlands are good at.
Okay. Maybe to wrap up the interview, I've two questions. One is on neutral atoms, and is that for neutral atoms they're scaling quite rapidly at the moment, but each individual atom needs to be controlled, and they do that with optics, and you are really good at controlling photons. Is there a synergy there? Would you be open to do so, or is that you say, well, that would be a distraction, and it would be a competing architecture on being a system integrator? Where does that fit in strategically?
Well, of course, I cannot divulge anything about the business strategy of QuiX at that level, but purely on the technological perspective, you're absolutely right that more and more other computing technologies are starting to realize that they need photonics and that they need quite high-end photonics in order to succeed, right? So as QuiX grows into a large scale, right, into a larger and larger company, it's very natural that any company asks itself, well, what else is all of the technology that we are sitting on, what else is that useful for, right? And so you can absolutely see that these kinds of things eventually might come into view.
Okay, thank you. And my last question, Jelmer, can you walk us through, if we meet again in 2030, what would success look like for QuiX Photonics quantum computer?
By that point, QuiX has established itself as the successful photonic quantum computing company in the world, right? So at that point, we have delivered a system that is big enough, that is powerful enough to show that scaling to a industry-size quantum computer is a no-brainer, right? That is really powerful enough, that is really obvious that we are the ones that are going to win. At that point, the company has grown. It has sold computers as test beds, right, all around the NATO alliance. And at that point, we are pushing, towards this industry scale deployment into data centers.